Our next speaker before the first break is Alex Endert, who is assistant professor in the School of Interactive Computing at the Georgia Institute of Technology. And he'll be presenting visual analytics by demonstration for interactive and immersive data analysis.
Okay, is that good? Excellent. First of all, thank you for hosting this event, to the organizers. I'm really excited to be here today and excited to share an interesting idea in a line of research that my students and I have been pursuing for a few years now called visual analytics by demonstration. First of all, if you look at a bit about me, you'll notice that there's not really a whole lot of VR or AR as part of my background. My formal training is a computer scientist. I studied a lot of things about information visualization, visual analytics, but mainly the idea of how we interact with visualizations and how we interact with, in many cases, machine learning models or data analytic models as part of how we do visual analytics. Throughout this talk, my hope is that I'll be able to inspire some ideas, perhaps for discussion or collaboration, on how we could leverage this new exciting technology to bring it into the field of visual analytics and, generally speaking, data science. So, in terms of starting the story, visual analytic tools are becoming a lot more complex. And that's in part a direct result of data complexities and data scales, right? We're grasping for more advanced and powerful machine learning and data analytic models to help us understand data of large scales, volumes, velocities, complexities, all those kinds of words to describe it. And as a result, there's been a lot of innovation over the years in analytic models and visualization techniques, right? We don't just use bar charts and scatter plots anymore. We have lots of different ways to visualize data, given the domain in which we visualize it, given the characteristics of the data, the distribution of the data, so on. And at the same lines, we have lots of sort of analytic models and machine learning models, which help us crunch through the data, if you will, right? George alluded to projection techniques, and we'll look at some of those in my talk as well, but there's certainly many, many other ones as well now. And I think that the two together, the analytic models and the visualization, lead to this really exciting research area of visual analytics. But the part where the story sort of begins for a lot of the research that I've been interested in is sort of this lack of innovation for user interaction. And to me, this is actually kind of scary when you think about it. And I'll show you a little story about that in a minute. But as we've innovated so much in terms of the technologies for data science and so on, the method to incorporate the user to do things like sense making, for example, are really still by and large the same traditional graphical user interfaces that we've had. And perhaps we need a disruptive technology like VR, AR to be able to get us out of that a little bit. And allow people to become a bigger part of that interactive sense-making loop. And to me, the ability to really think about the user interaction as a pivotal component of how we develop systems in this sort of fluid interaction term, as Nicholas Elmquist and others have coined, creates a sense of immersion during the data analysis. You become part of this joint system, not just a viewer of the result of something that a machine learning model spits out, or a viewer of a visualization that you could perhaps walk through or pan and zoom, but still are sort of on the receiving end as opposed to a central component of what it's like to do data analysis. So let me just walk you through this a little bit, right? InfoVis, something that's all near and dear to our heart in this community is the idea of show me the data, right? So this stacked bar chart here is a classic example of that kind of thing, where you're looking at over time. I believe this is a certain services running on a server, and you can see, oh, look, there was a lot of the blue stuff happening in the beginning, then more of the yellow stuff happening later on, a big spike in general, a bit later in the data. And we use our cognitive and perceptual system to really start to reason and come up with questions about this data. And then when I have a question like, why was there more blue in the beginning, or even what is the blue, I am led to, in many popular tools, a whole bunch of graphical user interfaces and control panels and drop-down menus and buttons and icons and other things that are really the affordances given to me to allow me to inject the things I want to ask, my hypotheses maybe, the things that I want to tell the system, right? Ooh, that blue, that was just a service that I'm not interested in. Delete it and give me a new representation. And many other things that really incorporate the user into this data analysis process. And the general idea here is let me interact with attributes of the data, right? I want to get rid of the blue thing because I'm an expert and I don't want that baseball service to show up on my server and how I analyze the load on my server, for example. And this has been studied by many people over many years, sort of this idea of direct manipulation interfaces as being really powerful ways to incorporate users into information visualization. And by and large, they are very, very effective at allowing people to change things like the visual mappings, right? Or the view transformations, or the way that we do data transformations to ultimately get from a data source all the way over to a view, and then the user who can interact with that view in a specific way. Well, it gets a little more tricky when you start looking at visual analytic interfaces. And so here we have a tool called IPCA developed by Remco Cheng and others. And it actually has a rather simple visual representation, right? It's a spatialization or a scatter plot. That's the result of a projection technique called PCA. And it's used to analyze high-dimensional data, right? For you to see perhaps some clusters or so on and so forth. And again, we've adopted, or the authors here did, the creators, adopted that same direct manipulation paradigm to allow people to interact and explore this data using this kind of an analytic model. And that can be done by directly weighting some of the dimensions, right? So say you care more about dimension 1 versus dimension 2, you can adjust the weight directly. You can also select which principal component you choose to map onto which axis. Now, this is where I typically, whenever I give this talk, say from the audience, raise your hand if you know the difference between choosing the first or third principal component of a PCA decomposition. All right, not bad. I typically get maybe about 2 people that are actually able to raise their hand on that. And that's great, except what does that do for the rest of the folks? And more so, what does it do for people who are domain experts and not data scientists? Right? It is very, very rare that I speak in front of a group of folks that are domain experts that can actually answer that question. But what domain experts do have is, well, domain expertise. So they know a lot about the data. They know about the data items. They know about the data attributes. They know about relationships of the data. They're really good at being able to ask questions of their data that are actually meaningful in their domain, as opposed to just spurious correlations between attributes, which may or may not actually be meaningful, even though they're statistically valid. And so this really sort of has started this process of us thinking about how we enable a different way for people to visualize, or for people to interact with visual analytic tools, where they can leverage their expertise on the data and the visualization that we've created, but not necessarily have to be domain experts in things like data science, right? So if we take this example here, where the typical interaction paradigm or process is actually interact with model parameters, adjust them. When you adjust, you hit go, you get a new visualization, and you may or may not see something interesting, but that's sort of general loop that's created there. What we've gotten really interested in is spinning that around and saying, well, how do we let people interact with the visualization and let the system come up with the appropriate representations or parameters of the models, in some cases even select the right model for the domain expert to use, given some hypothesis or some question that he or she may have, and actually show in the visual. So this has led us over the past several years to look at this concept of visual analytics by demonstration, which really has to do with incrementally augmenting a visualization to demonstrate some process or a part of a process or a question or a hypothesis to these mixed initiative visual analytics systems. And we use the mixed initiative term here to really imply that there is a give and a take and a balance of tasks of who does what between the user as well as the AI, the ML, the analytic models, the machine, right? Whatever the term is you want to use for that computational horsepower that we get from data science. And here are just some examples of the kinds of demonstrations and sort of primitives of demonstrations that we're looking at. And you can see they apply to a wide range of different visualization techniques. Things like clustering or dimension reduction, things like splitting or merging hierarchies, things like adding edges to graphs, and doing different kinds of graph modeling. And I'll just walk through a few examples of these kinds of techniques and tools that we've built. Well, we've built a lot of them, and I think the slide is out of date since the most recent Viz deadline. But you can see, sort of just from the distribution here, that a lot of our lab does focus more on, roughly speaking, the visual analytics side, where there is a significant component of a back-end machine learning model that helps produce the actual visualization, as opposed to just saying, you know, here is my spreadsheet, I would like to make a bar chart. And there's a direct mapping between the data and the view. But nonetheless, the techniques that we've developed actually apply to both, and you'll see examples of both of those. And I'm obviously not going to talk about every one of these, don't worry. So a simple start was actually during my time at Virginia Tech as a PhD student, was doing that exact sort of rotation of that particular example, which is to say, if I see a projection of data points where pairwise distance between data points computes to similarity, right? And I see two data points that are less similar than they look to be, I can simply drag them apart, right, to roughly the distance that I think they should be, and have the system compute the weights on the attributes or the principal components to use, or whatever it may be, to actually amplify that difference that I'm trying to impart into the system. Now, I'm not going to throw mathematical equations up here, but basically, this idea of imparting more similarity or more dissimilarity by moving points apart or closer together solves for the difference between the eigenvectors that you're actually dragging. All right, as mathematical as I'll get. So from there, we also looked at the issue of, again, projections, like George pointed out, which is it's very hard for people to understand what the actual axes mean on these projected scatter plots, right? It's not as simple as saying, oh, it's the price of something mapped to the axis, where further left means you know, more expensive, or that it's time going across one of the axes, where it's a lot more easy for people to understand what that actually means. Instead, often there's, in this case, for PCA, it's a linear combination of the weights of all of those all of the attributes that map to the axis. That's really difficult for many users to grasp about what it means for a point to be further on the left, or for what it means to be a point to be further on the right, or up versus down, and how that actually rotates and all these kinds of things. So we built a system called InterAxis. And what actually enables people to do is to, in one part, actually go down here and set the actual weights of the attributes, if they so choose to, similar to the IPCA tool. But also, if you see those green boxes at both extremes of the axes, people can actually drag points that resemble a certain category into one side of the axis and the other side of the axis, and points that are a lot like those two will start to go towards those axes as predicted or as computed by the difference between them. So, for example, you know, you might place a car. This is sort of our standard test data sets that we use towards the top of the axis. That's maybe some kind of all-wheel drive sports car that you like. And then maybe there's a car that you drove that you didn't like so much, and it was a rear-wheel drive wagon. You place it at the bottom, and you're starting to see how people can create, by demonstration, one of these sort of projected views that now have an inherent meaning to them, since they're the ones that were involved in the step of actually creating it, right? They're offloading part of their cognitive structure into this spatial representation, and in turn, into the underlying analytic model, right? You can then go on and do something similar to the other axis, if you'd like. Right? And now you start to see sort of a better clustering and a stratification of this space for items that probably have some sort of semantic meaning to the user. We have found a particularly interesting use case for this one, which is obviously figuring out which car you're going to buy next. But if you're doing that with your spouse, you can say there are cars that I like and cars that I don't like, and I drag them to one side of the axis. You have that your spouse do the other one on the other side of the axis. Can anyone tell me what this would look like if you two are in very good agreement on what kind of a car to buy? Yes, a 45-degree diagonal, right? Because your preferences, as computed by the model, would line up, and you would start to see that at the 45-degree diagonal across. Now, you can do other things, like saying there's cars I like, cars I don't like. Perhaps then also on one axis do cars I can afford, cars I can't afford. I don't know. But there's certainly the interesting thing about imparting some aspect of what you know about cars or what you want to know about cars into the model here and having that interplay work really, really well. I won't go into as much detail here, but we also more recently looked at how to do this with nonlinear models or piecewise linear models. So again, ramping up the complexity of the analytic and trying to maintain a similar kind of user experience of doing this kind of thing by demonstration, as opposed to literally diving deep down into the control panel and setting aspects of this model. So you can see that instead of having the price of a car count a certain percentage across the entire visualization, this axis rainbow, as we called it, actually shows how much certain attributes weigh at certain points across the axis. This was a lot harder for our domain experts to understand. We actually had a healthcare expert trying to analyze different patients using this, using a piecewise linear model as opposed to a linear model. It was still rather difficult for her to actually understand what we were trying to show with this. So you can see, ratcheting it up to complexity also sort of increases the or decreases the usability in some cases of domain experts. Oh, and here are some of the demonstrations that you can actually do in that tool. You can connect different patients, different data items. You can draw polylines between them as a path that you're interested in, or maybe a part where you see or would like to see some kind of separation between groups of patients, and then actually understand what kinds of attributes they share or actually make them different in order to gain some insight into your very high-dimensional data. Well, I'll say high-dimensional data. I think this had about 400 and something dimensions that you ultimately try to reduce down and understand. We've also done a lot of work on text visualization. And the reason I wanted to show this particular one is because of the data scale and complexity. So this was a project that we did that tried to visualize all of the content of English Wikipedia. So 4.656 million documents. In terms of data dimensions, there were about 850-something thousand dimensions of the data, right? So all the unique, meaningful words used across all of English Wikipedia, and some metadata as well. So you can see, as we really start to get into these very, very high-dimensional data sets, the challenge of user interaction becomes really, really prevalent in that. We used a similar kind of projection technique, as well as hierarchical topic modeling and some other techniques to really try to distill out what are the key topics across Wikipedia. And how do you let people tell the system the kinds of topics that they're interested in, or the kinds of relationships that they would like to see and explained, right? And what they would like more detail about, what they would like less detail about. As you can assume, we can't show everyone all of the topics being used because, well, we don't have enough screen real estate. And quite frankly, a lot of them may not have the same amount of saliency as you would expect to see from some other terms that you're interested in. So the user interaction that well, here's a zoomed out view. I don't know if I have a further zoomed out one. I don't think I do. But this was us just looking at it and seeing what kinds of topics and terms are often used across Wikipedia. And you can see larger words, similar to how word clouds work, are the ones who occur more often, and smaller ones are ones who don't. And users, and the distance here also encodes pairwise similarity between those topics as computed by the topic model we used. But users have the ability to change that a little bit to show what they're interested in. Right? So you can zoom out, you can pan, you can explore the space, you can then zoom in and say if you're really interested in this term and you'd like to see more about it, you can actually directly increase or decrease the size of it. And as a result of that, we go back to the back end and we fetch more terms that have to do with that sort of subtree of the hierarchical topic model that we used. And then, as a result, the trade-off is that you remove other terms, which fall off the leaves of the trees that you're not interested in, as a way to say we're trying to preserve only a certain amount of items actually shown on the screen at any given time, so we don't just create an information overloaded display. Graph modeling is another really complex domain, but one that our domain experts use quite a bit. So as you can imagine, what I mean by that is the ability to decide what constitutes an edge between data items. So if you have a graph and you have edges already, that's simple, right? They're given to you. But if you have data where relationship is inherently in the domain, but not given to you by the data, so the toy example we like to use is the IMDb movie data set, where there are relationships between movies, right? They may share the same actor, the same director, but there's no sort of given edge in the data set necessarily. But domain experts probably want to see graphs of that resemble those relationships. So instead of having them go through and do, SQL, please define your edge criteria, we actually just let them draw edges between nodes, actors, movies, so on, have the system solve for what are meaningful edge criteria, and then amplify that on the rest of the graph. So you can connect any two nodes, and from that you can then build up a graph that really, that models that kind of connection that you're looking for. So again, flipping around the way that we do that, as opposed to control panels, SQL queries, so on. And so if we take a step back and really start to think about this in terms of the context of why we're here today and some of those things, I really think that this places a different role on the visual representation, right? Whether this is in VR or whether this is on a desktop or a tablet or your watch, whatever, it's no longer an output-only representation. And the interaction is really central in this idea because we are now in the visualization, interacting as opposed to in the control panel. And this also creates challenges because systems can no longer assume specific, explicit, formal commands from users, right? You're no longer sliding that slider a certain distance and that means a specific value, or checking a toggle box that says I want to use this hyperparameter of my SVM as opposed to that other hyperparameter. But it follows the idea of sort of incremental formalism, which I assume some other speakers might talk about, a little bit more closely. And as such, I think is tailored a little bit more to how people want to make sense of their data and follow the sense-making model as such. So I promised I would bring you, that is not, well, that is one way to autocorrect Immersive. There you go. There you go. I guess that's why we're here today. So part of what really got me interested in immersive technology is the opportunity that it really affords people to be more expressive about their user interaction. We've talked about degrees of freedom. We talked about gestures. We talked about physically walking around, right? What we noticed is that simply using a mouse in order to have people, I don't know, drag points closer together or further apart or into buckets or into clusters or out of clusters, while that's great and while there's a lot of sort of usability advantages of using that, it's limited in the sort of expressiveness that people can give the system about what they're trying to accomplish. I guess my hypothesis is that as we start to allow people to have more expressive ways of interacting, more embodied ways of interacting, more immersive ways of interacting, we can start to really look at that richness of the sensor technology in AR and VR as new possibilities for how do we let users interact with machine learning in this kind of metaphor that we've talked about. So I know that I am literally keeping you all between coffee, so I will probably wrap up there. But I'm really excited about these technologies, and I'm excited about the conversations that we can have over the course of the day, and hopefully some of the collaborations going forward. I do want to, before I end, quickly say that a lot of the work, basically all the work I've talked about today, I didn't do by myself. My students at our lab did. And I'd also like to thank the sponsors of the folks who have helped make this work possible. Thank you.
Thank you, Alex, for a very interesting talk. So I think we can afford maybe just a couple quick questions so that people can go off to their break.
Alex,
yes.
I know it's early in the field, but has anybody made any breakthroughs looking at the data this way? I could just see somebody spending hours going, oh, this is cool, let me try this, let me try this. Is it too soon, or has anybody actually gotten some kind of breakthrough by using these kinds of tools?
So some of the domain experts we work with are able to discover things and gain insights into their data that I won't say wouldn't be possible without it, because it would, but it would be a lot more difficult and probably require a data scientist to help them do that. So for example, we are actively working with some physicians and allowing them to bin the data in these ways that make sense in their domain quickly and easily, allow them to see patterns in their particular data sets that otherwise they would be less likely to find, or would take them longer to find, or be more difficult. At what point some of this becomes a bit more mainstream, I don't know. But I think some of the things we're seeing from empirical results of studies that we do, we are seeing people, non-data scientists, be able to use these tools and get insights regularly. Yes?
Just a quick question. You mentioned hierarchies for the data and you're visualizing it, which to me very often refers to taxonomies, but sometimes you have multi-domain data, interconnections between them, which more or less to ontologies. Are you also building ontologies for your information and then try to visualize this cross-cutting nature of it?
It's an interesting point. We have not. I know some of my colleagues at Pacific Northwest National Labs are looking at that. There's some interesting things you can do about building up ontologies of that person's domain, right? Because they're interacting with a system, they're telling the system something about what they know, what they want to see, and actually if you can model that in terms of an ontology or other representations you can use for user models, you can really start to learn a lot about the domain by just having people explore data. And there's a couple of places that are funding some of our work that are really interested in that particular one, because they want to understand what makes an expert, and they want to quantify that somehow. And so there is the ability to do that as well.
Thank you.
No, thanks.
Let's thank all the speakers again.